Welcome to Recitation 7. Today we're going to talk about internal and external validity. So I think students usually use more points on the concepts or the choice questions, not the short answers. So these concepts are really important, not the calculations. It's never the calculations that matters. Okay, so we should answer a question like, what makes a regression reliable? So this is asking you, does it imply a causal effect? So essentially your beta 1, can it imply causal effect? So internal valid, it is internally valid if like it is you can say it is a causal effect for your studied population or for a given population. And it's externally valid if you can like extend it to another population. So a very good example of internally valid regression is, let's say you study whether your college degree can lead to higher wages, right? This is, if you design a good study, you can have a causal effect. And another failure of external validity is the you are trying to find a factor X that can potentially affect tomorrow's stock market price. And a lot of these studies and regressions are not externally valid. You cannot predict the future. And we will talk about 5 sources that internal validity can be violated. So we will use the simple regression case, and yeah, we only have one x1, only have one variable, and the conditional expectation of we will use this assumption. So conditional expectation of the error term given x1 should be 0, but we will talk about in 5 cases that this condition is violated. So the first one is your omitted variable bias. And this one, you have seen this a lot of time. And the solution to this is like adding more controls, right? And also, Professor will talk about the panel method and IB in the future. So essentially, the panel method is to it can help you control for like the time fixed effect and individual characteristics that are not changing over time. So what kind of person you are is not going to change over time. And the second one is the functional form misspecification. So this one's intuitive. So if you have a data like this, let's say a simple regression, you have a single variable to regress for x on y, and you can see you should use a quadratic functional form, but instead you use a linear regression like this. And of course your estimator is biased because you use linear term. And instead, if you use a2x2 squared, right, add a quadratic term, so the regression will look like this. So it's the big data better. So solution to like functional form misspecification issue is so you can either take logs or add quadratic terms or add interaction terms. And these are just the issues that I don't like it. So here, measurement error. This is my research area. Measurement error and sample selection bias. Like this. Okay, so let's see here. We have some formulas here. This can be a good multiple choice or a short answer question. So here we have measurement error. Let's say first we can have measurement error in y or measurement error in x, right? Let's say first we have measurement error in y, and y star, let's say is actual y, and y is the observed y. Let's use this too. Okay, let's define the error, measurement error to be the error is y, your observed y minus y star, so the actual y. You cannot observe this one. So your y is actually the actual y star plus the error. And then you run the regression. The observed y is beta 0 plus beta 1 x1 plus u and plus your error term, the measurement error. And this your error, like the normal u we normally discuss. So let's assuming that the expectation of u is 0, and this term, this u, is not correlated with x1. So the covariance of x1 and u is 0. And then let's say if the covariance of your measurement error in y and x1 is 0. So this measurement error and your x1 is not correlated. Then your OLS, so x1 and your measurement error in y is not correlated, so it does not affect beta 1. So intuitively, your beta 1 estimate OLS is still unbiased and consistent. But it has a larger variance. So let's say another strong assumption, your the covariance of the error term and your measurement error in y is 0, still 0. So let's say the variance of your new error term. You cannot observe this one, right? So your variance of the new error term, constant error, is larger than when you do not have the measurement. So what's the variance of two random variables? This should be variance of, it's the variance of u plus e is the variance of u plus variance of e plus 2 times covariance of, and we set the covariance of u and e is 0. This term is 0. And the sigma squared u is the variance of u, and sigma squared e is the variance of. This should be larger than, because all of these are possible. So sigma squared. So you, bottom line is you have a larger variance. But if your measurement error in y is not correlated with x, you shouldn't have a biased estimate of beta 1. And the problem is serious when you have a measurement error in x. So let's say your actual x, let's say it's x star, and this is your observed. So x is observed, third x. And we assume that the conditional expectation of u given your actual x is 0. And again, we define the measurement error index is the E1 is your observed x minus actual x, x1. And still, your measurement error is trivial, like the expectation of your measurement error in x1 is 0. And then you run the regression. Your y is beta 0 plus beta 1 times your actual x1 plus u. And then if if the covariance of your actual x and your measurement error in x is 0, then it must be the case because E1 is a function of your observed x. So then it must be the case that the covariance of your observed x and your measurement error in x is not 0. And what's the covariance? What's the formula for covariance? Is this covariance of x1 and b is the expectation of x1 minus expectation of x1 expectation. And we assume that expectation of e is 0. So this term is 0. So we only have expectation of x1 times e times e1. And this is, we can plug in for your observed x1. Your observed x1 should be the actual x1 star plus e1. So here we have the expectation of your actual x times your measurement error in x plus the expectation of your measurement squared. And this is 0 because we assume that the covariance of your measurement error in x and actual x is 0. So this one's 0. And the covariance of your observed x and your measurement error in x is the variance or variance of your measurement error. So if your measurement error is really large, like the variance of your measurement error is really large, it will correlate it to your x, and it can sort of bias your estimation of beta 1. So your OS estimate of beta 1 is biased and inconsistent in this case. I think this is the most important. I can assure you, probability this will be on the test is very high. And the fourth source of bias is the sample selection bias. So let's define MCAR is missing completely at random. Now in this case you have missing data. This is also my research area. So missing data, like we usually have manipulated data set, even the garment manipulated data. So if we have missingness and they're missing completely at random, it should be the case that covariance of your missingness and the error term is 0. And then your covariance of your missingness and x1 is 0. So missing is completely missing. So does not correlate with anybody. So when is when will this be violated? Is a good example is the online IQ test. So you can think about this example that if you want to study the effect of IQ on, for example, wages, only those who have a high IQ will take the online test. So your OLS in this case is biased because the covariance of your missing, like your missingness and your x1 is not there. So anytime you have an arrow, you have a missingness that is correlated with your dependent variable, like your independent variable, your x. If your x is correlated with missingness, correlated with measurement error, you will have a biased beta 1, biased estimate. And the last one is reverse causality. So in this case, we usually assume there's one way causal effect. So x affects y. But in a lot of cases, the model should be dynamic. So that means time is important. Time is very important. So in this case, the past can affect the future, and the future can affect the past because people have expectations. So the future can affect past. So it can be the case that y affects x, and x is also affecting y. So in this case, your OLS estimate is biased. And usually you argue for external valid, that you say, the study cannot be extended to another population or another time period. Then it's not externally valid. All right, that's all I gotta say. If you have any questions, you can come to me.